next, let's go to example 2.23. We're coming close to the end of this session where we will do some homework the first time in this course. So let's look at example 2.23, which is on page 169. Yep, page 169. I need to remember to write down the page because I later can't find it myself. It's like, where's example 2.23? So here's what you're supposed to do. You're supposed to evaluate the limit of a rational expression. Rational means it's a fraction of some sort. Okay, you will evaluate x minus 3 over x squared minus 2x at 2 from the negative side, from the side of less than 2. That is from the left side, right? So so how do you do this? There is your book shows you how to factor this thing, and then you take the limit of each chunk and figure out which way it's going. Now, if you look at it quickly, 2, if you plug in 2 here, 4 minus 4 is 0. So you're dividing by 0, which means that you got a problem. And unlike some other examples we've done, there's no canceling here. Sometimes you can cancel out the 0. That's the one big trick. But if you cannot cancel out the 0, then the game is then your limit doesn't exist. Okay. So what your book wants you to do is just figure out which way it's going. Because if when you're dividing by 0, it's going to infinity, well, positive or negative infinity is what you're looking for. Now you can do that, but there's a easier way, less work. That is, you can simply graph this thing. Now I have wrote down the link for the online graphics calculator, which is far better than this thing. Let me show you this. Okay, this is called the graphics calculator. I hope by the time you look at this video, this thing's already gone extinct. Not that I have anything against Texas Instruments, I don't. But it's a real pain, okay? The online calculator is much better. And being that my class is a math as a hobby class, not, you're not taking, not for you to pass some test, I would recommend that you don't bother with this. This costs me a lot of money too. So let's look at the online. If you type this stuff online, at the, what is this thing called? At the Desmos website or some other one that you can find. And you just type this thing in. I should mention that, okay, the way you type it in like this. You type in everything in parentheses. Okay, here's how you type. You type in parentheses x minus 3 close parentheses divided by x parentheses again x raised to the power. This button is the button that's 6. You have to push shift. Okay, push shift and 6 will give you that button. That is the raise to the power button in math. And then push 2 and then type in minus 2x. You don't have to type in multiply or anything. This thing is super smart. So anyway, at the Desmo website, which I will write down the link below the video, it will immediately pop out this graph that looks like $1,000,000. And the Desmo website says they make beautiful graphs. They're not kidding. It really is, especially compared to the TI-84. This. I mean, this thing has pixels, for heaven's sake. Do you even know what pixels are? If you don't, it's like Minecraft, except much worse. Anyway, so let's make a beautiful graph. So I graphed it on my computer, and you can type it in yours or something at Desmos, and you will see something like this. Let's see. It goes down like that. This approaches an asymptote. That thing goes like this, and then here's another chunk that's going like this. All right. So, but all we care about is at 2. Where's 2? 2 is where 2 is this particular asymptote. Mm, yeah. Okay. So 2 is somewhere before here. Okay, where you have this thing called an asymptote. Asymptote. Toped. Well, whatever. The point is, you're approaching from 2 minus. So here's 2, and so you're approaching from this side, and you can see that it's going to positive infinity. And that's that. Okay? It goes positive. The limit is positive infinity, period. Ah, good enough. But anyway, so next. But you should probably also look at how the book does it. It just factors, so it doesn't have the draw graph. But I think is either way. I find the graph way much easier because of decimals calculate online calculator. And the other way, you have to figure out minus and then multiply by plus. Does minus multiply by plus yield a plus or minus? I don't know. Well, move along. Right. Next, let's look at the squeeze theorem. The squeeze theorem is a very intuitive theorem that says something like, okay, let's look at squeeze theorem, page 171. The squeeze theorem says something like, you have 3 functions, okay? So 3 functions, so they're called f of x and g of x and h of x, and for some reason, you can prove that in a small neighborhood that this relationship is true. To what? In a small neighborhood around a certain point called A, that this relationship is true. So on the real line, you have A here, and there's a small area. It doesn't have to be big. In other words, it doesn't have to be, f of x doesn't have to be less than g of x all the time. It just has to be in a small neighborhood around the number A. Why? Because A is all, this small area is all we care about. We're not interested if this is, if f got bigger than g some other place. Yeah, we don't care. Okay, we only care about at A. Now, if this relationship is true around a small neighborhood next to A, then we say this. That's the first condition. The second condition is you happen to be able to prove that this limit as x approach A of f of x it exists and equal to some kind of number, okay, that is not infinity, is a number, L, and it limits goes here, and this, and the same thing here. Limit of h also becomes as x approach A also is L. So these 2 points are going to the same place for some reason. If that is true, then it's intuitively obvious that the limit of g of x as x approach A has to equal to L, okay? Because it's stuck between these 2 things, and these 2 things are coming to a fixed point, approaching a fixed point, then this thing has no choice but to go to that point too, because it's stuck between. It can't get less or more or nothing. So it's kind of like if you have 2 cars, and you're the car in the middle, 1 car in front of you, 1 car behind, and at some point in time, the 2 cars decided to drive at the same speed, like 10 miles an hour. You are not allowed to pass them. Okay, you are stuck between, you have to stay before that guy and after that guy. So then eventually you're forced to go at 10 miles an hour as well. You have no choice. So, yeah. All right. So that's the squeeze theorem. The squeeze theorem is good for proving some limits that is not obvious, but it's not obvious where it goes, but you can find other limits that you do know where it goes, and you can find them such that the unknown limit got stuck in the middle. And if you can control that, then you can squeeze it and say it goes to where you want it to go, or where you think it's going. All right, so that's the end of the squeeze theorem. Now, after the squeeze theorem, your book talks about something very interesting, but to me is not relevant at this point. So, so I'm gonna do this part is about your book is gonna talk about something like sine theta is less than theta is less than tangent theta. This thing. Which I thought about this, and I decided that I will talk about this as an extra project at the end of this class. When we finish the class, I want to finish the class, and so I also recommend you to do so. If you have extra time, you finish today's class and you want to look at this thing, that's fine. But if you haven't finished the day's class, do it first and then do the extra stuff. I will present this thing once we finish calculus 1 and have a celebration. So we'll celebrate by doing some projects such as this thing. So moving on. Um, okay, that's the end of section 2.3, and I would like you to, at this point, do homework. Homework is very, very important in calculus. It's pretty time consuming, but you're talking about calculus here, okay? It's considered one of the toughest class in college for good reason. It's time consuming. But time consuming and difficult are not necessarily the same thing. I mean, for example, if somebody's forcing you to wash 100 toilets, that would be very time consuming, but you can probably do it if you have to, right? Hopefully you never have to do that. I mean, hopefully I never have to do that because, but but I have washed my toilets 100 times over the years. It adds up. It can be done. Okay, anybody can do it basically. But is time consuming. Calculus is very time consuming. So I would like you to do the homework, and first let me tell you which homework to do. I've chosen with some care about 12 problems from the exercises. So please do homework. The homework is on 2.3, okay? 2.3, which is yeah. Homework is on 2.3, which is on page 176. And there are 12 problems, and I will list the problems below the video, but I'll read it out to you now, which is 83, 89, 97, 99, 100, 102, 105, 111, 117, 120, 126, and 127. I would like you to finish the homework before you move on to the next video. It's very important to finish the homework. Now, being that you are teaching yourself calculus, and this book has the answer keys of all of the problems. So after you're done, look at the answer keys. The first question anybody asks is, well, but what if I don't know how to do it? If you don't know how to do it, I want you to give up to an hour per problem that you can't do, and hit it with everything you got. You know, if your life depended on it, and you got 1 hour to solve this problem, can you do it? That kind of thing. And instead of, I discourage anybody from the second, I don't know how to do that, you come running off to your teacher, to your brother, to somebody who's good at math online and post a problem. Oh, please help, I don't know how to do this. Put in the hour first. After that, okay, if you still want to, if you can't get in, okay, maybe ask help. Or maybe anything that you don't know how to do, put it in a file. It's like your cold case file for detectives, right? And when a detective get a murder case, he studies it, he investigates, he gives it a fair share of time and try to solve the crime. Sometimes he does, sometimes he doesn't. And the crimes that they can't solve, the detective put it in his code file and maybe look at it later. And that's what I encourage you to do. is because what matters here is not that you got help and somebody else showed you how to do this. You need to do it yourself. That's the beauty of calculus, is to actually doing it. That calculus is like basketball. You need to go practice shooting the hoops or dribble it around or whatever you call basketball. I don't know much about basketball and can't stand it. But you need to play it. Just watching the NBA games all the time, it's not going to help you be good at basketball yourself. It might help you talk about it and look like you're knowledgeable, but at the end of the day, you might not even be able to get out of bed, let alone shoot a basket. So to be good at calculus, you really need to do the homework. It's very, very important. So I picked your book has about 40 problems. I picked about 12 of them. Right now, we are still at the beginning stage. The problems are not particularly difficult. But it shouldn't take too long to do it. But if it does, do them. But before that, don't forget to redo all the examples I did. And once you are done with the problems, and well, redo the examples first, right? Practice, and because they will prepare you to do the problems. Now, once you're done with all that, if you want to do some of the examples that I didn't cover, that's fine too. But you have to watch yourself and be very careful that you don't. That is, you don't overkill. And the reason is because to I want to draw you something. Well, first, I should mention that I'm a mathematician. I'm also a efficiency expert. Efficiency principles dictate this. Let's see. This is the efficiency principle. It's like a bell curve. It is. It probably is the bell curve. The point is here. This point is where you're lazy. Okay, this is the lazy people. Lazy people don't do their homework. They who wants to do homework? Nobody wants to do homework. So lazy people don't get their homework done, and when they don't get their homework done, they can't get through the class. Even if they continue to watch videos, it'll just get harder and harder because they haven't done it, and eventually they just kind of have to collapse. Now, on the other side of the bell curve, this is the greedy people. They're also called hardworking, okay? But in reality, hardworking people are greedy. What's wrong with greedy people? The greedy people are the ones that do more than is required. They just, oh man, this is great. This stuff is great. I love calculus. And you only assign me 12 problems. I can do more. I'll do 24. I'll do 40. I'll find another calculus book and do another 100. Those are the greedy people. The problem with greedy people is that they tend to burn out. Okay, they just take a big rush. They're all worked up in the beginning. We're only in chapter 2, the beginning of calculus. They're all excited, and then they took too much, and then they collapsed, and then they never do calculus again. So they just like the fireworks. There's a big old flash, and then it's gone. So you do not want to be the lazy people because you didn't do anything. You don't want to be the greedy people either. The greedy is a trap because nobody wants, calling people lazy is an insult. But the greedy people are often called hardworking, which is a compliment, and therefore people get trapped into being greedy all the time. Okay, and then they collapse. What you want to be, here's this is where you want to be. This point, this is called optimum. What's optimum? Optimum is the best spot that you do everything you that needs to be done, but not much more. Okay, you stay here. Why? Because that way you got the stuff done. You're not lazy. Okay, but on the other hand, you're not so greedy that you wore yourself out and collapsed. You didn't collapse. You conserved your energy. You paced yourself. In long distance running, there's something called pacing yourself. Don't just start dashing the second you get out. We're doing a marathon here. Calculus is a marathon. Well, it's more than that because even a marathon is done in a few days. You're gonna take more than a few days to do calculus. So what you want to do is find your optimum point. What is your optimum point? That's different for each person. For one person, they might be young, energetic, healthy, and got nothing to do, and unemployed. They got lots of time, and they love math. Their optimum point might be 5 hours a day of calculus. For somebody else, who you maybe you're old, you're a retired doctor, you made your money, now you're retired and you want to study calculus or restudy calculus. Um, your your optimum point might be just an hour a day. It depends on individual person. So it's your responsibility to find your own optimum state. It could be doing calculus 3 hours a week, kind of like a regular college class, or it could be 7 hours a week. You do it every single day, or 5 hours a day every day. You can totally do that because you got the energy. But whatever it is, you need to use it wisely, okay? Because here's some news. You don't have unlimited time. You don't have unlimited energy. Your time is precious. Your energy is precious. Your interest is precious. Your focus is precious. They are all limited values. So when they are limited, you need to budget them like money and spend them in the wisest way, in the most beneficial way possible, and not waste it. Okay, do not waste it on, say, studying all the problems in chapter 2, and then you're so tired that you don't want to even look at chapter 3. Then you just collapsed. Again, that's kind of also like it's kind of like the story of the tortoise and the hare, right? I mean, the hare was running very fast in the beginning, and it was so fast that it collapsed. It was worn out, so it has to take a nap because it overstretched itself. Then the tortoise was slow, but it went steady and eventually made it to the end. Now, I don't want you to be the tortoise or the hare. The tortoise is too slow, the hare went too much, gone too far. I want you to be the optimum. Who is optimum? Optimum is called Goldilocks. Remember Goldilocks and the Three Bears? If you don't know what I'm talking about, Google it, find out. It's a very important story, a kid's story that sounds silly at first. Goldilocks goes to the bear's house, and she's rest. She needs to take a bed, go to sleep. She got into the first bed, it was too soft. She got into the second bed, it was too hard. And then she got into the third bed, it was just right. So that's where I want you to be Goldilocks, which is the optimum point, where you study not too hard, not too little, too easy. Okay, then just whatever is the optimum point that will get you to the end of this course. And so that's that. So please go do the homework and pause this video and get your homework done. And afterwards, I will then come back to this video at this point because I will talk about some of the homework probably. Let's see. I want to say there's something else I want to tell you about homework. Each time you do homework or think about doing homework, remember this. Doing homework is like wrecking your car or going broke. There is no perfect time for it. So please go do the homework now and pause the video. Let's see, where is my video? So now that you're done with the homework, let's talk about a couple of them. I want to talk about 97, problem 97. This is exercises 2.3. Page 176, and I need to take the cap off my marker. All right, I got it. So again, we're on page 136, and now I'll talk about some homework. Make sure you've already done with it, because it doesn't do much good to watch me talk about it if you've never done it yourself. So, what's this? Now, let's look at problem 97, where it says, is the limit as t goes to 9 of t minus 9 and the square root of t minus 3. So as you can see, What that means is you have a 0 divided by 0 situation, right? T is going to 9, that's 0, that's also 0. So the way you fix this situation when you have a 0 divided by 0 situation is you by factor and hopefully cancel the 0 out. So what you do is this very handy theorem, right? You have to do this. This has a name. It's called difference of squares, right? Difference of squares, but use the difference of squares trick, okay? Where a here will be the square root of t, and b will be 3. Then t itself will be a squared, and 9 will be b squared. And you follow that theorem. I mean, this thing, whatever this equation, difference of squares. So you have, then you factor this thing, it becomes the difference, square root of t plus 9, and then you have t minus 9. All right, and 3. What am I saying? You take the square root of 9, which is 3. Let's do 3. That's better. Okay, t minus. So the square root is 3, and then the whole thing's divided by t minus 3. And as you can see, there's another one on top, so which means you can cancel it. That's what you're hoping for. See? And so you can cancel out the 0. As t approach 9, the square root of 3 approaches 3, but it's not 3. It only approaches it. So it's like, what is it? It's like maybe 3.001 or 2.99999. Whatever it is, it's not 3, okay? But it's very close. As long as it's not 3, it's perfectly legit to cancel it. So, so then this equal to limit of square root of t plus 3 as t approach 9, and that value comes up to be 3 plus 3 is 6, and that's your answer. As is quick and clean. Okay, next problem that I want you to do is 105. All right, 105. I'll write it down here. Problem 105. There's 4 problems. There are 4 problems at 105, which is the limit of as x approach something. In this case, is 1. X approach 1 from the negative side, or the left side, the lesser side, of 2x plus squared plus 7x minus 4, and divided by something, x squared plus x minus 2. As x approaches 1, 1 plus 1 minus 2 is 0. So you can see that there is a thing happening here. But the problem is, the top might not equal to 0, because as x minus approach 1, that's 2 plus 7 is 9 minus 4 is not 0. So you're not going to be able to there's nothing to cancel out. That is, you won't be able to cancel out the 0. So this thing will go to infinity. But which one? Is it positive or negative? You can factor it out and do what the book says in that example 2.23 or something, or we can graph this thing on the Desmos, the beautiful online Desmos calculator, graphics calculator, which I have graphed it. And you type this thing in, right? Remember, to do the raise of power, you have to press shift and the 6 button, because the 6 button has that thing on top, and that's the raise to the power symbol. So once you type this in, the Desmos will immediately show you this thing right here, which I will draw it out. Let's see. Okay, I have typed it in earlier. Something like this, I guess. Okay. Okay, so it has, you notice that this thing, when x is 1, y is 0, so there's an asymptote at 1. 1 is all we care about right now, but we can do all 4 problems in this group the same way. So here's 1, so you have asymptote at 1, right? Well, as x approach 1, what happens? Well, it goes down. See, this is the part that matters. So the answer is minus infinity because it went down. Now, and we can do all the others too. What happens if x approach for the positive side? Here's 1, right? But let's say x approach this way, then you follow this graph, and if x approach 1 from the positive side, then it goes to positive infinity. See, it goes all the way up. At least that's what Desmo says, and we trust them. So it's much easier. See, there are 2 more problems. -2, which is over here, is a similar situation. Here's another. At -2, this thing also goes to 0. So here's another asymptote. This is also an asymptote situation. Oh, and then so at -2, it going from the left side, it goes negative infinity. Going from positive side, it goes to positive infinity. So with that, we finish all 4 problems from 103 to 106. Yeah, so moving on. The last problem I want to talk about is, where is it? Okay, 127. Flip to 127. It says problem that 127 wants you to calculate this thing. Limit of okay, theta goes to 0 of theta squared times cosine of 1 over theta. All right, and you're supposed to apply the squeeze theorem. Well, let's just say this. As x at this particular, when you type it into the decimals thing, it probably let you type in theta, but I don't know. But let's just type in x. Okay, one variable is as good as another. So, but I'm not even going to do that because this is the function theta squared cosine of this thing is less than just theta itself, theta squared, which is bigger than 0. Okay, and this is your f of x in the squeeze theorem. That's g of x and that's h of x. And as theta goes to 0, then 0 stays there. 0 doesn't go anywhere. It just stays 0. And this thing goes wherever it goes, right? If theta goes to 0, theta squared also goes to 0, right? So you have 2 zeros, so which proves that this thing will go to 0, period. Yeah, and I put in the absolute value here to get around the fact that sometimes this value is negative. But we don't really care. It's good. Positive or negative is going to 0, so it's good. And that's the end. And that's the end of section 2.3. And if you haven't done your homework, please go do it. Because remember, doing homework is like wrecking your car or going broke. There is no perfect time for it. So do it now.